For this problem, we have a point that is chosen at random from a circle that's centered at the origin with radius r. So let's start drawing the picture. So here we have a circle with radius r, at least something that looks like a circle with radius r. And the question is, first off, to find the joint PDF of x and y. And it's chosen at random. So at random doesn't say so, but it means uniformly between somewhere inside of the circle. So first off, it's uniformly chosen. So f of xy has to be equal to a constant. Now, how do I find that constant? That constant will be 1 over the area, in the same way that for the uniform distribution, it's 1 over the length. So as discussed in class, this will be constantly 1 over the area of the circle, which will be pi r squared. And this is true as long as x squared plus y squared is less than or equal to r squared. And of course, it is equal to 0 if you choose a point that is outside of the circle. So it's uniformly distributed, and so that's going to be the PDF. My constant value as long as I choose a point inside of the circle. Okay, so next off, let's find the marginal density for f of x. So for my marginal density for f of x, I choose a point x, and then I integrate with respect to y. So if I pick a value of x, that means that y squared is equal to r squared minus x squared. And so the two values of y will be plus or minus r squared minus x squared. That'll be the top and the bottom y coordinates. So the marginal PDF for x will be equal to the integral from the bottom x coordinate to the top x coordinate of the joint PDF with respect to y. So that'll be equal to y over pi r squared, evaluated between these two endpoints. So plugging in, we get square root of r squared minus x squared minus negative square root of r squared minus x squared divided by pi r squared. And that works out to be 2 times the square root of r squared minus x squared over pi r squared. Now, the one last detail is, what is the possible values of x? Well, x can be anywhere along this line here. And of course, it's got radius r, so the smallest x can be as negative r, and the biggest can be as positive r. So this is the density as long as negative r is less than or equal to x, less than or equal to r. So that's the answer for number 2. Number 3, let d be the distance of the point from the origin. Find the probability that d is less than or equal to a. This one is actually surprisingly easy if I just simply draw the picture. So let's draw the circle again. And I want the distance from the origin to be less than or equal to a. So that means that I fall somewhere inside of a circle that has that radius a. Well, the chance of falling inside of the circle, if everything is uniform, and that's a big if everything is uniform, then it's simply going to be the area of the small circle divided by the area of the big circle. So pi a squared over pi r squared, which is simply a squared over r squared. And this holds as long as a is between 0 and r. That my a here, the radius, is something that's positive, but no bigger than the radius of the big circle. So this one I could do without any direct integration. It's uniform, so it's going to be area divided by area. Lastly, the problem asks for the expected value of d as well as the standard deviation of d. So to get that, let's figure out the the density function. So the CDF works out to be a squared over r squared. And so the PDF will therefore be 2a over r squared, as long as a is between 0 and r. Now, we've been typically using x as opposed to a, but there's nothing wrong with using the letter a here. So there's my PDF for the distance from the origin. So therefore, the expected distance from the origin will be integral from 0 to r of 2a squared over r squared dA. Now this looks a little funny because it's not an x, but there's nothing wrong with the letter a. So we're doing the integral, we get 2/3 a cubed evaluated from r to 0, and that works out, and I forgot the r squared in the bottom. So that's 2 times r cubed over 3r squared, and so that works out to be 2/3 times r. Sorry, that went off the screen. So the expected value of d is equal to 2/3 times r, just figuring out the expected value. To figure out the standard deviation, we first figure out the expected value of d squared. So that's integral from 0 to r of 2a cubed over r squared dA. So that works out to be 1/2 r squared in the bottom also, a to the 4th from r to 0. So that's r to the 4th over 2r squared, which is 1/2 r squared. And therefore the standard deviation of d is equal to the square root of 1/2 r squared minus 2/3 times r squared. So that's the square root of 1/2 r squared minus 4/9 r squared, which works out to be r over the square root of 18, or r times 3 over the square root of 2. Okay, so that's the standard deviation of d. So except for me blowing it with the camera, for the computation of the expected value of d, that's the calculation. So for the way we did this, we got the CDF first, then we got the density function, then found the appropriate integrals in order to figure out the expected value and the standard deviation.